So in the coming minutes, I'll talk you through EVPN gateways to scale EVPN fabrics. So it's all about EVPN. So I'm curious, who of you in the audience is familiar with EVPN, heard about all these route types? Please raise your hand. I think we have a pretty good coverage. But I still prepared the first slides as a short refresher. What are we talking about if you talk about EVPN? So first, EVPN is a control plane protocol. It's an extension of BGP. We have a new, well, by now it's not new anymore, address family called EVPN, and we can use this to implement layer 2 and layer 3 services over an underlay. Well, underlay, it's the data plane, and it's specified for different data planes that you can operate over it. Most commonly, you see it with MPLS and VXLAN. That really boils down to that. And in contrast to many solutions from different vendors that were common before we had EVPN in the data center, well, it was often proprietary layer 2 fabrics. So this is a big shift because this is our open standards and regular interop tests happen. So this really interoperates between different vendors. Within this EVPN address family, as you might heard, we talk about different route types to signal different things we have in the network to build these layer 2 and layer 3 VPNs. So we use, for example, route type 2 to signal MAC addresses or also all ARP entries. We use type 5 to implement layer 3 VPNs to announce IP prefixes. We have 2 route types that we use together, like number 4 and number 1 for multi-homing, all signaled through EVPN. And then there's also route type 3, which we actually use to communicate where are the other tunnel endpoints. So this is kind of really quick, the foundation. So if we, with this foundation, build bigger EVPN-based solutions, we have, among others, 2 challenges if we scale bigger. Well, the first that we have here is if we have 2 data centers and maybe there's some form of backbone, maybe an MPLS backbone in between, how can we provision a service from data center 1 to data center 2 without maybe cumbersome VLAN handoffs between a PE router and our fabric? How can we build really end-to-end services? That's one challenge where EVPN gateways help us. And the second one is if we build really large fabrics. Say you want to build a data center fabric with 1,000 leaf switches. There is a lot of state within EVPN. And how can we make this to actually work to scale to such sizes? So these 2 challenges, we're looking into it and how EVPN gateways help us dealing with them. Again, the solutions for EVPN gateways, they are based on open standards. There are several. We're diving mostly now into 2 of these standards. One is used to implement layer 3 services and the other for layer 2 services. There are some standards that are not really adopted. So most vendors that implemented EVPN gateways base their solutions on these orange marked standards. So again, for these 2 challenges that we want to talk about, one, the DCI solution, so interconnecting 2 data centers. It's now our border leaves that also implement this gateway functionality and talk to the gateways, to the border leaves of the other data the other end, the other data center. And the transport in between can be just an IP transport, can also use VXLAN or MPLS, maybe in combination with segment routing. This is all standardized and tested. And then the other is to scaling to a big single data center by dividing the whole fabric into different pods and adding EVPN gateways at the edge of each pod and connecting them through a superspine layer. We'll dive a little bit deeper how this actually works. So the basic functionality of the EVPN gateway to actually help with scaling is to introduce hierarchy into the whole EVPN fabric. So here we have gateway 1 on the left and the gateway 2 on the right. In between, again, some backbone network. Maybe it's also with VXLAN, maybe it's also with MPLS in the underlay. Now, the routes that the gateway receives from its local data center, when it announces them or re-announces them to the other side, to gateway 2, it sets the next hop as itself. That's kind of the basic mode of operations. So that the data center on the right basically receives these routes then from its local gateway and not from all the switches, from all the VTAPs from data center 1. That's kind of the first approach. And if we use, for example, MPLS, then it's also the duty of this gateway to, on one hand, act as PE and serve the MPLS part of the network, but at the same time also speak VXLAN to the local data center and thus the DCAP and NCAP with the other data plane protocol. So with this, we can, even though if we have a change in the underlay protocol, still provision a seamless service end-to-end over these different underlay networks. Of course, this solution is not limited to just 2 networks or 2 data centers that you want to connect with gateways. If you have, well, as depicted here, 4 data centers, it might make sense that they all peer to a common set of route servers or route reflectors, depending on how you architect your protocols. So you don't need a full peering mesh of these BGP EVPN sessions. Now, I like to dive a bit deeper first into how we implement layer 3 VPN, layer 3 EVPN gateways. In this example, we have VTAP 1 or VTAP 2 that originate a prefix. Again, we want to implement here a layer 3 service. And gateway 1, which also participates in its local data center, receives this route. When it's advertising or re-advertising this to gateway 2, it sets itself as next hop. That's the basic operations. And gateway 2 then does basically the same thing before it advertises this prefix to the VTAPs in the local data center. So with this, we also build some hierarchy. The VTAPs in the remote data center do not need to know all the loopback addresses, all the tunnel endpoints from the local data centers. So this is already a big step into scaling further with EVPN. Now, how does this look from a forwarding perspective? Here we receive, on VTAP 1, it receives a frame from host 1 on the left, encapsulates that in a VXLAN header with gateway 1 as destination address. When gateway 1 receives that, it decapsulates, does a lookup, and figures out, oh, actually, I need to send this to gateway 2 because it's from the remote data center. It re-encapsulates the data frame into VXLAN again, but this time it sends it to gateway 2 and sends it from its own address. Gateway 2 then does the same. So you see, we do not only have some mechanisms in EVPN, but there also are some operations required on the data plane because the gateway does decap and then encap again. Now, if we look at the route type, at the data that is exchanged through BGP, the gateway actually copies most of the data from this route, but it updates the next hop, potentially the label or the VNI, and also the router MAC. It uses its own router MAC to originate what it advertises. The other things are basically just copied normally. Of course, if you put that at the edge of your data center and you want to interconnect your data centers, you don't want to do this without redundancy. So typically, these EVPN gateways are deployed in pairs. And then both of them, just when they announce something to the other end, do the same thing. They set the next hop to their own address. Now, an issue could arise if gateway 2 receives the updates of gateway 1 for the same prefix, and then decides, oh, I have another path. Maybe let's even do ECMP directly to the remote end, but also to gateway 1. That would certainly not be ideal. So for that, either we need to implement some policies to, for example, change the preference from routes we receive from the other gateway, or implement dpath or the domain path community. This then acts in a similar way to an AS number in eBGP. And it would help to prevent that we create routing loops here. Now, this was all about layer 3, and initially you could see that for layer 2, there is actually a different RFC. So it's a different section in the presentation, and there's also a little bit more going on for EVPN gateways for MAC-VRFs or layer 2 services. So again, well, type 5 routes we already discussed. We have certain routes that are just locally significant. So for the multi-homing, type 1 and type 4, they are just not re-announced by the EVPN gateway to the other end. The type 2 with the MAC addresses that we advertise, they are re-originated, but again, with the next hop of the gateway. And the type 3 routes kind of also re-originated, but just using the VTAP address of gateway 1. With this, we also achieve that we can reduce the number of route messages that actually land in the other data center, and with that, we also help the protocol to scale better. The other effect that actually we reduce the flood lists. So if gateway 1 only sets itself as next hop and advertises only the type 3 route for itself and not for VTAP 1 and VTAP 2, we actually now have shorter flood lists, which again helps with scaling, especially also if we build really large fabrics, and then it really helps to reduce the flood lists. Because this is also coupled with limited resources we have on the ASIC. So it's better there is a finite amount of how big flood lists we can have depending on the ASIC we use. Actually, on the forwarding plane, it's very similar into what we looked before for a layer 3. It's the gateway which forwards the frame but re-encapsulates with itself as the source and destination the other gateway. So very similar in principle to the layer 3 use case. With resiliency or redundancy, we have multiple options. One is we work with MLAG. So with MLAG, we have just one pair that we can use as gateways that we can combine. They need a link in between. But we can only have one MLAG domain per site. Then there is a solution where we just use multiple, it can be more than 2 gateways, and configure an anycast address for the VTAPs. And the traffic from the data center, from the remote data center, will then load balance among these gateways using ECMP. So it's also quite useful. But with this solution, we cannot connect hosts directly to the gateways, which is possible with an MLAG solution. And then probably the most elegant solution is using EVPN multi-homing all active, so that we actually use the EVPN routes to signal that these gateways form a multi-homing gateway instance. And if we compare that to MLAG, the benefit is we don't need any peer links, but can also scale or can build something with more than 2 gateways. So because we add redundancy, we need to talk about loop prevention once again. With MLAG, this is relatively simple because both MLAG members use the same VTAP IP address. So if they receive the EVPN updates from the peer, they would simply not use them. It's invalid because they use an IP address. They use my own IP address, so it's not valid. And actually, the same is true if I use the second model, because they all use the same anycast address, so they would not accept the update from the other gateways. Now, with the last option, it's a bit different, because here, every gateway has its own VTAP address. So actually, they would accept the update from the other gateways, and the loop could form through that. Again, we would either apply routing policies to mitigate that, or implement the path community. Now, if you look how to set this up in EOS in the config, it's actually pretty simple. When I define the neighbors for the EVPN address family, I can kind of mark there that this neighbor or this group of neighbors is actually from the remote domain. This is one thing. And then for the service, here it's a layer 2 service, VLAN 10. Again, for RD and also for the route target, I have the option to specifically mark it with the remote domain. And I can either choose to use the same sets of route targets for remote and local, or I can also use a different set of route targets and have all the flexibility with that, if I would choose to do so. So that is the basic mode, how this works. Now, probably the biggest question is, when do you actually need it? With which size of your deployment do you reach the point where you actually are required to implement EVPN gateways or everything would fall apart? Unfortunately, there is not a super easy answer because it's a multidimensional problem. It depends on how many VTAPs you have, how big is your flood list, in combination with how many services are you configuring, how many layer 2 and layer 3 verbs do you actually configure, and then how many MAC addresses and how many prefixes per VRF. So it's a combination of all these factors that you need to take into consideration to decide if you need an EVPN gateway or not. But maybe in general, if we talk about an EVPN fabric with 20, 30 leaf switches, usually it's not a topic, but if you start to growing and you approach 100, 200, or even more leaf switches, and you have a lot of services there, then it's certainly worth it that we discuss if it makes sense to add EVPN gateways. So as a super short summary, what is an EVPN gateway doing with different route types? So with type 1 and 4, which are used for EVPN multi-homing, it's not forwarding them to the other side, because the idea is you have, in the local data center, you have servers connected redundantly with a port channel, and you don't need to signal this to the other end. We have type 2 routes for MAC addresses or ARP entries, and the gateway re-advertises them with its local, with its own MAC and IP address. And the same is true for the type 5 prefix. And the type 3 routes, we do not let all the local type 3 routes over to the remote data center. It's only the gateway that announces its own type 3 route to the other end. So this is actually just the first part, because you might know there are many more route types. For example, to deal with multicast, and then there is also a solution how to implement EVPN gateway for multicast. But I guess that's for another day. Thank you very much.
Thank you. Are there any questions?
Ivan Piepelnjak, IP Space. Just a question on the loop prevention, where you mentioned we need the extra attributes. Can't we do loop prevention on the AS path, like regular BGP?
Depends on your design.
Of course.
But if you use eBGP in underlay and overlay, then, and also with EVPN multi-homing instead of MLAG, then every VTAP has its own AS number, and then you don't have that.
Yeah, but still the gateway wouldn't accept its own looped path because it has its own AS number in the AS path.
Correct.
Right?
Correct. But it's the second gateway has a different AS number.
Oh, you should know that. Thank you.
More questions? Nope. Then thanks again very much.